In 1979, a young physicist named Alan Guth was working at Cornell University. He was trying to solve some nagging problems with the standard Big Bang model. On the night of December 6th, he had a breakthrough. He developed an idea he called cosmic inflation. The theory proposed that in the first fraction of a second after the Big Bang, the universe underwent a period of incredible exponential expansion. It grew from a size smaller than a proton to something astronomically large in an instant. This idea beautifully solved the problems he was working on, like why the universe is so uniform and flat. But it also had a staggering implication. It meant the universe is not just what we can see. The observable universe, with its billions of galaxies, is just a tiny, insignificant patch in a much, much larger cosmos. The total universe can be trillions of times larger than what we will ever be able to detect. This provides a stark and simple solution to the Fermi paradox, the question of where is everybody? The answer might be that we are profoundly, unimaginably alone. The distances created by inflation are so vast that no civilization, no matter how advanced, could ever cross them. We might be the only thinking beings in our entire cosmic horizon. If that's true, then the story of this solar system, our solar system, is the only story that matters for life as we know it. And that story has a definitive, violent, and fascinating end. It is a story written by the life and death of our star, the Sun. Number 20, Silence and Darkness Reign Forever. The timescale for a white dwarf to cool into a black dwarf is around 1 quadrillion years, over 100,000 times the current age of the universe. When our sun becomes a black dwarf, its surface temperature will be less than 5 Kelvin, just a few degrees above absolute zero. If the theory of proton decay is correct, even a black dwarf will eventually evaporate over a timescale of 10 to the power of 37 years, leaving literally nothing behind. The final state of our solar system is not fire, but ice. It is not a bang, but an endless, silent fade to black. After the sun has shed its layers and collapsed into a white dwarf, it begins the longest and most uneventful phase of its existence. A white dwarf is the hot, dense core of a dead star. It has no internal source of energy. It is a cosmic ember glowing with leftover heat from a life of nuclear fusion, and it spends the rest of eternity cooling down. This process is incredibly slow. A white dwarf is about the size of Earth, but it contains the mass of a star. This density means it holds a tremendous amount of thermal energy, but its small surface area means it radiates that heat away very inefficiently. It's like a perfectly insulated thermos flask the size of a planet. For trillions and trillions of years, it will hang in the center of our solar system, a tiny, dim light source. The surviving planets will continue their silent orbits around it. They will be frozen solid, their atmospheres long since condensed into ice on their surfaces. The solar system will be a ghost of its former self, a collection of dark, cold bodies moving through the void. But even this state is not permanent. The white dwarf continues to cool. It fades from brilliant white to yellow, then orange, then a dull red. Eventually, after a length of time that makes the current age of the universe seem like a fleeting moment, it will radiate away its last accessible heat. It will no longer glow. It will become a black dwarf. A black dwarf is a theoretical object because the universe is not old enough for any to have formed yet. It is the end of the line for a star like our sun. It is a cold, dark, incredibly dense chunk of degenerate matter, likely carbon and oxygen drifting in space. It emits no light, no heat. Its temperature will be almost indistinguishable from the background temperature of empty space itself. The solar system will be utterly dark. The planets, if they survive the gravitational nudges of passing stars over these eons, will be nothing more than frozen rocks orbiting a gravitational anchor point. There will be no energy, no change, just the slow, cold dance of celestial mechanics in perfect blackness. This is the true end. The fires of the red giant phase are a distant memory. The beautiful planetary nebula has long since dispersed into the interstellar medium. The brilliant white dwarf has faded. All that is left is a cold, dark graveyard. a collection of objects that were once a vibrant system teeming with energy, now inert and silent for the rest of time. The final word in the story of our solar system is darkness. Number 19. The sun becomes a diamond in the sky. A typical white dwarf is so dense that a single teaspoon of its material would weigh about 15 tons on Earth. The pressure at the core of a white dwarf can be up to 100 million times the pressure at the core of the Earth. As the white dwarf, sun cools below a certain temperature, around 10 million Kelvin, the carbon and oxygen atoms inside will lock into a rigid lattice structure, a process identical to crystallization. Long before our sun becomes a cold black dwarf, it will undergo a remarkable transformation. It will turn into a crystal. This is not science fiction. It is the predicted outcome of physics under extreme pressure and temperature. A white dwarf is composed mostly of a sea of electrons and a soup of carbon and oxygen nuclei. The only thing preventing it from collapsing further under its own immense gravity is something called electron degeneracy pressure. The electrons are packed so tightly together that quantum mechanics forbids them from getting any closer. This is a very stable but very strange state of matter. As the white dwarf radiates its heat away over billions of years, it cools down. When the temperature drops to a critical point, a phase change occurs. The intense pressure forces the carbon and oxygen nuclei to stop moving around freely. They lock into place, forming a body-centered cubic crystal lattice. Essentially, the entire core of the dead sun crystallizes. The result is an object the size of a planet made almost entirely of a single massive crystal. Given that the primary component is carbon, this means our sun will become a diamond. An Earth-sized diamond. Astronomers have already found evidence of this process. A white dwarf named BPM 37093 in the constellation Centaurus has been observed to be pulsating. These pulsations are like seismic waves traveling through the star. By studying them, scientists have concluded that a large portion of its interior has already crystallized. They nicknamed the star Lucy after the Beatles' song Lucy in the Sky with diamonds. Our own sun will follow the same path. For billions of years, it will hang in the center of the dead solar system, not just a glowing ember, but a glowing crystalline sphere. It will be the most valuable jewel in the universe, a diamond weighing more than 100,000 Earths. But there will be no one to see it. Its light will be faint, and its gravitational field will be the only thing holding the frozen remnants of the planets in their orbits. This crystalline state has an effect on its cooling. The process of crystallization, like freezing water, releases latent heat. This will temporarily slow down the white dwarf's cooling rate, postponing its eventual slide into a black dwarf for another few billion years. It is a final small burst of energy from a star that has long since exhausted its nuclear fuel. The idea of our star, the source of all our life and energy, ending its days as a colossal diamond is a strange and beautiful one. It is a testament to the exotic physics that govern the universe at its extremes. The solar system will be a dark and frozen place, but at its heart will be an object of incredible structure and density, a final solid form for the star that once burned so brightly. Number 18, a new, feeble light source emerges. A freshly formed white dwarf, like the one our sun will become, has a surface temperature of over 100,000 Kelvin, far hotter than the sun is today. Despite this intense heat, it is so small, about the size of Earth, that its total luminosity is less than 1% of the current sun's. This high-temperature, low-luminosity object will emit most of its energy not as visible light, but as extreme ultraviolet and X-rays. When the sun finally casts off its outer layers as a planetary nebula, what is left behind is the core. This core, a newly born white dwarf, will become the new center of the solar system. But it will be a very different kind of star. It will be incredibly hot, but also incredibly small. This combination creates a bizarre new environment for the surviving planets. The heat is intense, but you have to be very close to feel it. The planets that were not destroyed, like Mars, Jupiter, and Saturn, will be in orbits far too distant to receive any meaningful warmth. From Jupiter, the white dwarf sun would appear as an intensely brilliant pinpoint star, like an arc welder's spark in the sky. It would provide far less light than the full moon does for us today. The solar system will be plunged into a deep twilight. The surfaces of the gas giants, which are colored by complex chemical reactions driven by sunlight, will change. Their vibrant bands and storms may fade into a more uniform, muted appearance. The remaining icy moons, which may have briefly had liquid water oceans during the red giant phase, will freeze solid again, harder than granite. The little heat the white dwarf produces will not be enough to sustain any liquid on their surfaces. The nature of the light will also be different. Because of its high temperature, the white dwarf will emit a harsh blue-white light rich in high-energy radiation. Any object remaining in the solar system will be sterilized by a constant bath of ultraviolet rays. This is not a life-giving light. It is a harsh, sterile glow. Over billions of years, the white dwarf will cool and its light will change. It will fade from blue-white to pure white, then to yellow, and finally to a dim red. The overall brightness of the solar system will continuously decrease. The slow dimming of this central star will be the defining feature of the solar system for the next trillion years. The system's dynamics will also be simpler. The solar wind, the stream of particles that once flowed from the sun, will be gone. The heliosphere, the magnetic bubble the sun creates, will have collapsed. The solar system will be directly exposed to the interstellar medium for the first time in its life, where cosmic rays from distant supernovae will bombard the planets unimpeded. The new solar system is a stripped-down, skeletal version of its former self. A tiny, hot, dying star at the center, orbited by a handful of frozen, irradiated worlds. It is a stable but dead configuration that will persist for eons. Number 17, the system is filled with a ghostly nebula. A planetary nebula has nothing to do with planets. The name was coined by William Herschel in the 1780s because they look like fuzzy, planet-like disks through his early telescopes. These nebula expand at a speed of about 20 to 30 kilometers per second. Even at this speed, it takes thousands of years for them to disperse into the interstellar medium, meaning they are a very short-lived cosmic phenomenon. The gas in a planetary nebula is incredibly thin, often less dense than the best vacuum chambers created on Earth. After the sun exhausts the helium in its core, it will enter its final, most unstable phase as a giant star. It will swell up again, even larger and more luminous than before. During this phase, its outer layers will be held only weakly by gravity. It will experience a series of thermal pulses like giant stellar burps that push its atmosphere out into space. Eventually, the entire outer envelope of the sun, containing nearly half its original mass, will be ejected. This expanding shell of gas is what we call a planetary nebula. For a few thousand years, our solar system will be encased within a beautiful, glowing cloud. The source of the glow is the hot, exposed core of the sun, the new white dwarf at the center. The intense ultraviolet radiation from this tiny star will ionize the expanding gas, causing it to fluoresce in brilliant colors, primarily the greens of oxygen and the reds of hydrogen. The sight from one of the outer planets, if one could see it, would be breathtaking. The sky would be filled with a luminous, intricate web of gas and dust. This would be the most spectacular and also the final act of the sun's life. But this nebula is not just a pretty light show. It has physical consequences for the remaining parts of the solar system. The planets will be moving through this thin but present gas. This will create a tiny amount of drag, causing their orbits to very slowly decay. The effect is minuscule, but over thousands of years it could be measurable. More significantly, the nebula is made of the very stuff that once constituted the sun's atmosphere. This includes hydrogen, helium, and heavier elements like carbon, nitrogen, and oxygen that were forged inside the star. This material will temporarily enrich the environment of the outer solar system. It will rain down on the gas giants and their moons, adding a new thin layer of material to their atmospheres and surfaces. The planetary nebula phase is fleeting. The gas will continue to expand and cool. Within about 10,000 to 20,000 years, it will have spread out so much and become so thin that it will no longer be visible. It will merge with the vast, cold emptiness of interstellar space. The material that was once part of our sun will go on to mix with other gas clouds, eventually becoming part of the raw material for a new generation of stars and planets, billions of years in the future, far away from here. Our solar system will have given its matter back to the galaxy. Number 16, the planets drift away. According to Newton's law of universal gravitation, the orbital period of a planet depends on the mass of its star. As the sun loses mass, its gravitational pull weakens and the planets will spiral outwards into larger orbits. The sun is expected to lose about 45% of its total mass during its red giant phases. This means a planet like Jupiter, currently at 5.2 AU, would end up in an orbit beyond 9 AU. The sun's death is not just a story of changing light and heat. It is also a story of changing gravity. As the sun evolves into a red giant, it sheds a huge amount of its mass. This happens through a powerful stellar wind, far more intense than the solar wind we experience today. Over hundreds of millions of years, the sun will blow nearly half of itself away into space. This has a direct and profound effect on every object in the solar system. The gravitational force that holds the planets in their orbits is determined by the mass of the sun. As the sun's mass decreases, its gravitational grip on the planets weakens. In response, the planets will begin to move outwards. Their orbits will expand. This is a slow, steady process. Earth, if it survives being engulfed, will not stay at its familiar 1 astronomical unit. Its orbit would expand to around 1.8 AU. This might seem like a saving grace, a way to escape the expanding star. But the sun's expansion is far more dramatic than the orbital migration. Earth will still be in grave danger. The real survivors are the outer planets. Mars will move from its current 1.5 AU to about 2.7 AU. The asteroid belt will expand. Jupiter will find itself orbiting where Saturn is today. Saturn will move out to nearly the original orbit of Uranus. The entire solar system will become a larger, more spread out version of itself. This orbital expansion will have secondary effects. The carefully balanced gravitational dance of the planets and their moons will be disturbed. The widening orbits could destabilize the asteroid belt, sending a new shower of rocks careening through the solar system. The orbits of Jupiter's and Saturn's moons could be altered. Some might be thrown into new eccentric paths, while others could be ejected from the system entirely. The Kuiper Belt, the reservoir of icy bodies beyond Neptune, will also expand. The whole architecture of the solar system, which has been stable for billions of years, will be redrawn. When the sun finally settles down as a white dwarf, it will be a much lighter star, with only about 55% of its current mass. The surviving planets will be locked into their new, wider orbits around this dead core. The solar system will be a more spacious, colder, and emptier place, its inhabitants held by a much weaker gravitational tether than before. This weakened grip also makes the entire system more susceptible to disruption by passing stars over the subsequent eons. Number 15, the solar wind becomes a hurricane. During its asymptotic giant branch AGB phase, the sun's mass loss rate will skyrocket to about 10 raised to the power of 7 to 10 raised to the power of 5 solar masses per year. This is 1 million to 100 million times greater than its current mass loss rate through the solar wind. The speed of this superwind will be slower than the current solar wind, only about 10 to 20 km/s, but its density will be enormous. This wind will carry away complex molecules and dust grains, including silicates and carbon compounds forged in the star's atmosphere. The solar wind we know today is a tenuous stream of charged particles flowing from the sun at high speed. It shapes the magnetospheres of the planets and defines the boundary of our solar system, the heliosphere. But when the sun becomes a red giant, this gentle breeze will transform into a raging storm. As the sun swells, its surface gravity becomes much weaker. The outer layers of its atmosphere are no longer held tightly and can escape much more easily. This creates a stellar wind that is incredibly dense and powerful. It is less a wind and more a continuous, massive outflow of gas. This superwind will flood the entire solar system. The planets will no longer be orbiting in a near vacuum, but through a substantial gaseous medium. This will have a drag effect, but more importantly, it will directly impact the planets themselves. The gas giants, Jupiter, Saturn, Uranus, and Neptune, will feel this wind most directly. They are massive enough to accrete, or capture, some of this material. Their atmospheres will be supplemented with gas that was once inside the sun. This will change their chemical composition, adding more hydrogen and helium, but also traces of heavier elements cooked in the sun's core and dredged up to its surface. Saturn's rings, which are made of almost pure water ice, will be particularly vulnerable. The constant bombardment of gas and dust from the superwind will erode the ring particles. The rings could be sandblasted away or contaminated with darker, dustier material, losing their famous brightness. Any object without a strong magnetic field or a thick atmosphere will be scoured. The surfaces of moons and asteroids will be directly exposed to this dense, slow-moving plasma. Their surface materials will be altered, and any remaining ices will be quickly vaporized. This superwind is the primary mechanism by which the sun loses mass and paves the way for the planetary nebula. It is the process that pushes the planets into wider orbits. For the duration of the red giant phase, the entire solar system will be a very different environment, not empty space, but a dense, dynamic sea of gas flowing outwards from the dying star at its center. The familiar clear void between the planets will be gone, replaced by the sun's own substance, filling the system before being cast off into the galaxy. Number 14, the heliosphere collapses. The heliosphere, the magnetic bubble inflated by the solar wind, currently extends out to about 120 AU, far beyond the orbit of Pluto. This bubble shields the solar system from about 75% of the high-energy galactic cosmic rays that would otherwise enter. When the sun becomes a white dwarf, its stellar wind will cease almost entirely, causing this protective bubble to shrink and collapse completely. For its entire life, our solar system has lived inside a protective cocoon. This cocoon is the heliosphere, a vast bubble in interstellar space created by the sun's magnetic field and the outflowing solar wind. It acts as a shield, deflecting charged particles from deep space, known as galactic cosmic rays. These particles are remnants of supernovae and other violent cosmic events. The heliosphere is our shield against the harsh radiation of the galaxy. When the sun dies, this shield will disappear. As the sun transitions from a red giant to a white dwarf, its mass loss and stellar wind will eventually cease. The white dwarf that remains will have a magnetic field, but it will not produce a significant solar wind. Without the outward pressure of the wind to sustain it, the heliosphere will collapse. The boundary between our solar system and the interstellar medium will move inwards past the orbits of the outer planets until it is gone. For the first time, the planets and other bodies of the solar system will be directly exposed to the raw galactic environment. They will be bombarded by the full, unmitigated flux of cosmic rays. Any surviving moons or planets will have their surfaces irradiated. This radiation can break down chemical bonds, altering the composition of surface ices and rock. It can darken surfaces over time. It can also erase any record of the past that might have been preserved in those ices. The collapse of the heliosphere also means the solar system becomes open to interstellar gas and dust. As the system orbits the center of the Milky Way, it will pass through various interstellar clouds. Without the heliosphere to push this material aside, it will flow directly into the solar system. This could lead to a very slow accretion of new material onto the outer planets and could create a faint haze within the system. The end of the heliosphere marks a fundamental change in the character of the solar system. It ceases to be an isolated, protected island and becomes just another part of the wider galactic sea. The cold, dead worlds orbiting the white dwarf will be subject to the whims of the galaxy, no longer under the protection of the star that gave them birth. This exposure to the harshness of interstellar space is a final step in the system's dissolution. Number 13, the Kuiper Belt awakens. The Kuiper Belt is a vast disk of icy bodies extending from the orbit of Neptune at 30 AU out to about 50 AU. It is thought to contain hundreds of thousands of objects larger than 100 kilometers across and trillions of comets. The total mass of the Kuiper Belt is currently estimated to be only about 1/10 the mass of the Earth. The intense heat of the red giant sun will be strong enough to sublimate ices like nitrogen, methane, and even water ice on these distant objects. The Kuiper Belt is the deep freeze of our solar system. It is a realm of icy worlds like Pluto, Eris, and Makemake, which have been in a frozen, dormant state for billions of years. The sun is so distant from there that its light is just a bright star, and its heat is negligible. But when the sun becomes a red giant, this will change. The red giant sun will be thousands of times more luminous than it is today. Even at the distance of the Kuiper Belt, the increase in heat and light will be dramatic. The sleepy, frozen worlds of the outer solar system will be baked by a level of energy they have never experienced before. The ices that make up their surfaces, frozen nitrogen, methane, carbon monoxide, and water will begin to sublimate, turning directly from solid to gas. These quiet, icy bodies will essentially become giant comets. They will develop massive atmospheres and long tails of gas and dust pointing away from the bloated red sun. The entire Kuiper Belt will light up, transforming from a dark, invisible region into a brilliant, chaotic swarm of activity. This mass sublimation will have several consequences. The outgassing will act like small rocket thrusters, altering the orbits of these objects in unpredictable ways. The gravitational stability of the Kuiper Belt could be shattered, objects could be thrown into the inner solar system, creating a late, final, heavy bombardment. Other objects could be ejected from the solar system entirely. The surfaces of these worlds will be permanently transformed. They will lose a significant fraction of their mass as their volatile ices boil off into space. What remains will be a core of rock and less volatile water ice, covered in a dark crust of organic compounds left behind by the sublimating methane. Pluto might be transformed from a bright, icy world into a dark, rocky one. This awakening of the Kuiper Belt will be a temporary but spectacular event. For a few 100 million years, the outer solar system will be a far more dynamic and chaotic place. It is the final burst of activity from the most distant and pristine part of our solar system, a direct response to the death throes of the star it has orbited for its entire existence. Number 12, the asteroid belt scatters. The total mass of the asteroid belt between Mars and Jupiter is only about 4% of the mass of Earth's moon. The four largest objects, Ceres, Vesta, Pallas, and Hygeia, account for half of the belt's total mass. The gravitational influence of Jupiter is the main reason these asteroids never coalesced into a planet, and it will also be the main driver of their scattering during the sun's death. The asteroid belt is a region of rocky debris, the leftovers from the formation of the solar system. Its objects are held in relatively stable orbits, shepherded by the immense gravity of Jupiter on one side and the Sun on the other. This stability will be broken when the Sun becomes a red giant. There are two main factors that will disrupt the asteroid belt. First, the expanding Sun's intense radiation will heat the asteroids. This can cause a phenomenon known as the Yorp effect, where the uneven radiation of heat from a spinning, irregularly shaped asteroid can alter its rotation speed. A faster spin can cause some asteroids to break apart. More significantly, the sublimation of any trapped water ice within the asteroids can create small jets, pushing them into new orbits. Second, and more importantly, is the changing gravity. As the Sun loses mass, all the planets, including the powerful Jupiter, will drift outwards. The shift in Jupiter's position and gravitational influence will wreak havoc on the delicate orbital resonances that structure the asteroid belt. Asteroids that were in stable orbits for billions of years will suddenly find themselves in unstable ones. Their orbits will become eccentric and chaotic. This will lead to a massive scattering of the asteroid population. Some asteroids will be flung into the inner solar system. This could create a final intense bombardment period for Mars and any remnant of Earth. Any moons that survived around the giant planets could be struck by these wayward rocks. Other asteroids will be thrown outwards, perhaps into orbits that cross paths with the outer planets. A significant fraction of the asteroid belt's mass will be ejected from the solar system entirely, sent drifting into interstellar space as rogue objects. What is left of the asteroid belt after the red giant phase will be a much more diffuse and depleted version of its former self. The gravitational reshuffling will clear out large portions of the belt, leaving only the most stable survivors in a wider, more spread-out configuration. The asteroid belt, as we know it, a dense collection of primordial rocks, will effectively be dismantled. Its contents will be scattered across the solar system and beyond, a final dispersal of the building blocks that never quite made it into a planet. As number 11, the gas giants lose their colors. The vibrant colors in Jupiter's atmosphere are caused by chromophores, chemical compounds that absorb certain wavelengths of light. These are thought to be complex sulfur, phosphorus, or carbon compounds created by chemical reactions driven by the sun's ultraviolet light and by lightning from powerful storms. Saturn's more muted, hazy appearance is due to a thicker layer of ammonia ice clouds that veils these deeper colored layers. Jupiter and Saturn are defined by their beautiful swirling bands of color. These colors are the result of complex chemistry happening in their upper atmospheres, chemistry that is powered by energy from the sun. When the sun's output changes, so will the appearance of these giant planets. During the red giant phase, the situation becomes extreme. The bloated sun will bake the gas giants with thousands of times more energy. This will dramatically heat their upper atmospheres. The increased temperature and intense radiation will drive new, powerful chemical reactions. The existing cloud layers of ammonia, ammonium hydrosulfide, and water ice will be disrupted. The deeper layers of the atmosphere will be churned up. The colors of the planets can become much more intense and chaotic. New, previously unseen chemical compounds could form, creating a palette of colors we have never observed. The familiar belts and zones could be replaced by a more turbulent, uniform appearance. The famous Great Red Spot on Jupiter, a storm that has raged for centuries, could be disrupted or fueled to an even greater size by the influx of energy. But this is a temporary state. The real permanent change comes after the red giant phase, when the sun becomes a faint white dwarf. With the primary energy source almost gone, the atmospheric chemistry of the gas giants will grind to a halt. The temperature in their upper atmospheres will plummet to incredibly low levels. The compounds that create the colors will no longer be produced. The existing chromophores will likely be destroyed by cosmic rays over long periods, or will settle out of the atmosphere. The dynamic weather patterns will cease, the winds will die down, the atmospheres will become stagnant and cold. Without the colorful chemical clouds, the gas giants may revert to a bland, uniform appearance, perhaps a pale blue or gray, reflecting the simple composition of their main atmospheric gases, hydrogen and helium. Uranus and Neptune already have this appearance because they are so far from the Sun that their chemistry is less active. And Jupiter and Saturn will eventually come to resemble them, but as much colder, darker, and more quiescent versions. The vibrant, dynamic worlds we see today will become static, colorless globes in the faint twilight of the dead sun. Number 10. The Great Melting of the Outer Moons. Europa, a moon of Jupiter, is believed to have a liquid water ocean containing more water than all of Earth's oceans combined, kept liquid by tidal heating from Jupiter. This ocean is sealed under a thick crust of ice, possibly 10 to 30 kilometers thick. Saturn's moon Titan has a thick nitrogen atmosphere and lakes of liquid methane and ethane on its surface, with a surface temperature of 179 degrees Celsius. In the outer solar system, where the sun's influence is weak, lie some of the most intriguing worlds. Moons like Jupiter's Europa and Saturn's Titan are currently frozen solid, or, in Titan's case, have rivers of liquid methane. The sun's red giant phase will utterly transform these places. As the sun's luminosity increases 1,000-fold, the temperature in the Jupiter and Saturn systems will rise dramatically. The habitable zone, the region where liquid water can exist, will move outwards. For a few 100 million years, the moons of the outer planets will be in the heart of this new habitable zone. The thick ice shell of Europa will melt. For the first time in its history, its vast subsurface ocean will be exposed to the sky. Europa will become a true water world, a global ocean under the light of a giant red sun. Ganymede and Callisto, Jupiter's other large icy moons, will also likely develop liquid water oceans on their surfaces. In the Saturn system, the changes will be even more exotic. Titan's thick nitrogen atmosphere will be heated, and its surface temperature will rise above the freezing point of water. The methane and ethane that currently form its lakes and rivers will evaporate, but the water ice that makes up the moon's bedrock will melt. Titan could become a world with a nitrogen atmosphere and deep oceans of liquid water, possibly mixed with ammonia. These newfound oceans will not last. The red giant sun is unstable. It will also be blasting these moons with a powerful stellar wind and harsh radiation. The new atmospheres and exposed oceans will be subject to intense erosion. Water molecules will be broken down by ultraviolet light, and the hydrogen will escape into space. Over millions of years, these moons could be stripped of their water, leaving behind dry, barren husks. This period represents a fleeting final chance for complex chemistry, and perhaps even life, to arise in our solar system. These moons have the key ingredients: water, organic compounds, and now a powerful energy source. But the window of opportunity will be short and violent. Once the sun collapses into a white dwarf, the habitable zone will vanish. Any liquid water that remains will freeze solid again, this time for good. The brief, spectacular summer of the outer moons will be over. Number 9. Earth becomes a cinder. Even if Earth's orbit expands to 1.5 AU, the red giant sun's luminosity will be so high that the equilibrium temperature on Earth's surface would be over 1,000 degrees Celsius. Tidal forces from the nearby sun would also likely lock the Earth's rotation, causing one side to permanently face the star, baking it even more intensely. The energy dumped into the Earth by these tidal forces alone would be enough to melt the mantle. The ultimate fate of our own planet is one of the most debated aspects of the sun's death. There are two main possibilities, and both are catastrophic. The first is that Earth is completely engulfed. As the sun swells into a red giant, its outer edge, its photosphere, will expand to somewhere around the orbit of Earth. Some models predict it will expand just short of Earth's current orbit, while others have it expanding beyond. If our planet is caught within the sun's tenuous outer atmosphere, it will not be instantly vaporized. Instead, it will experience immense atmospheric drag. This drag will cause its orbit to decay rapidly. Over a few thousand years, it will spiral inwards deeper and deeper into the sun. It will be torn apart by tidal forces and heat, its constituent atoms absorbed into the stellar furnace. In this scenario, Earth is simply erased. The second possibility is that Earth narrowly escapes being swallowed. This could happen if the sun's mass loss is rapid enough. As the sun sheds its outer layers, its gravitational pull weakens, and Earth's orbit migrates outwards. If it moves out fast enough to avoid the expanding photosphere, it survives, but survival is a relative term. The planet would be orbiting a star that is thousands of times brighter than the one we know. The surface of the Earth would be sterilized and scoured. The oceans will have boiled away long before this point. The atmosphere will be stripped away by the intense solar wind. The surface rock itself will melt. The Earth will become a barren, tidally locked ball of magma, with one side perpetually facing the hellish glare of the red giant. The day side would be a molten ocean, while the night side might be just cool enough for a solid, but still incredibly hot, crust to form. All traces of life, all evidence of our civilization, all the mountains, continents, and geological history would be wiped clean, melted down into an undifferentiated slag. When the sun finally shrinks into a white dwarf, what is left of Earth will cool down. It will solidify into a dry, airless, charred rock, a silent, dead planet orbiting a dead star. Whether it is consumed or merely burnt to a crisp, the Earth we know will be gone forever. And number 8. The inner planets are erased. Mercury orbits the Sun at an average distance of 0.39 AU. Venus orbits at 0.72 AU. The maximum radius of the Sun during its first red giant phase is predicted to be between 1.2 and 1.5 AU. Both Mercury and Venus are well within this zone of destruction and have no chance of survival. The first casualties of the Sun's expansion will be the innermost planets, Mercury and Venus. Their fate is sealed and not subject to the same uncertainties as Earth's. They are simply too close. As the Sun begins its transition into a red giant, its core contracts and heats up, causing its outer layers to swell. This expansion is not instantaneous. It happens over millions of years. But from the perspective of the inner planets, it is an unstoppable tidal wave of fire. Mercury will be the first to go. As the Sun's edge approaches, the small, rocky planet will be subjected to unimaginable heat. Its surface will melt. Then, as it enters the Sun's thin outer atmosphere, the chromosphere, it will start to experience drag. This will cause its orbit to decay. It will spiral inwards towards the denser, hotter regions of the star. The intense tidal forces of the Sun will stretch and deform the planet, pulling it apart. Mercury will be shredded into a stream of molten rock and metal before being completely vaporized and absorbed by the Sun. Its atoms will become part of the star that is destroying it. Venus will follow soon after. Despite being further out, it is still well within the red giant's eventual reach. Its thick, toxic atmosphere will be stripped away first by the intensifying solar wind. The planet's surface, already hot enough to melt lead, will become a sea of magma. Like Mercury, Venus will be caught by the Sun's expanding atmosphere, its orbit will decay, and it will be torn apart and assimilated. The destruction of the two inner planets will add a tiny amount of heavy elements to the Sun's convective outer layers. This is of no consequence to the star, but it marks the definitive end of two worlds that have been part of our solar system for over 4.5 billion years. For any observer in the outer solar system, the process would be invisible, lost in the overwhelming glare of the expanding Sun. The solar system will be permanently reconfigured, its innermost members simply erased from existence. Number 7. Mars's fleeting spring. Today, the average surface temperature on Mars is a frigid 63 degrees Celsius. For liquid water to be stable on its surface, the average temperature would need to rise above 0 degrees Celsius. As the aging Sun's luminosity increases by 40% over the next 3.5 billion years, Mars will be pushed into the center of the migrating habitable zone, receiving as much energy as Earth does today. This period could last for several 100 million years. Long before the sun swells into a red giant, its slow, steady brightening will have profound consequences. One of the most fascinating is the potential for a temporary rebirth of Mars. The sun is a stable star, but it is not static. It is fusing hydrogen into helium in its core, and as it does, the core becomes slightly denser and hotter. This causes the sun's overall energy output to increase. The rate is about 10% every billion years. This means in the future, the sun will be hotter and brighter. As this happens, the solar system's habitable zone road, the region where a planet can sustain liquid water on its surface, will slowly migrate outwards. Earth is currently in the middle of this zone, but in about 1 billion years, the increasing solar energy will trigger a runaway greenhouse effect on Earth, boiling our oceans and rendering our planet uninhabitable. But as Earth becomes too hot, Mars will just be warming up. The red planet will move into the center of the habitable zone. The increased sunlight will warm its thin atmosphere and frozen surface. The vast quantities of water ice locked in its polar caps and buried underground will begin to melt. This could release enough water to form rivers, lakes, and perhaps even small oceans. The sublimating carbon dioxide from the poles could also thicken Mars's atmosphere, creating more pressure and a stronger greenhouse effect, which would help to keep the planet warm. For a period of hundreds of millions of years, Mars could become a temperate, water-rich world. It would be a planet with a second chance at life. Whether life would actually arise, there is unknown. It may be that the Martian environment, even when warm and wet, lacks other key ingredients. And Mars's lack of a global magnetic field would mean its new, thicker atmosphere would be slowly eroded by the more intense solar wind from the aging sun. This Martian spring will be a temporary affair. As the sun continues to brighten on its way to the red giant phase, the habitable zone will keep moving outwards. Eventually, Mars too will become too hot. Its new oceans will boil, its atmosphere will be stripped away, and it will be baked into a dry, sterile desert once again. But for a brief geological moment, our solar system might host 2 habitable planets, one dying and one being born. Number 6, the sun's color will change. The color of a star is determined by its surface temperature. Our sun's surface is about 5,778 Kelvin, which produces a spectrum of light that our eyes perceive as white, though it peaks in the green part of the spectrum. A red giant star has a much cooler surface temperature, typically between 2,200 and 3,200 Kelvin. This lower temperature shifts the peak of its light emission into the red and infrared parts of the spectrum. When we think of the sun's death, we often focus on its size, but one of the most fundamental changes will be its color. Our star, the familiar white-yellow sun, will become a deep dusky red. This change is a direct result of the physics of a dying star. As the sun runs out of hydrogen fuel in its core, the core will contract and heat up. This superheats the surrounding shell of hydrogen, which begins to fuse at a furious rate. This new intense energy source pushes the outer layers of the star outwards, causing it to expand enormously. As the star's surface expands, it also cools down. The same amount of energy is being spread out over a much larger surface area. This is why a red giant is both incredibly luminous, producing thousands of times more energy overall, and has a cool surface. A star's color is directly tied to its surface temperature. Hotter stars are blue or white. Cooler stars are orange or red. The sun's surface temperature will drop by several thousand degrees, shifting its color from the familiar white to a deep orange, and then to a brooding red. The quality of light in the solar system will be completely different. It will be the light of a perpetual fiery sunset. The illumination on the remaining planets and moons will not be the harsh, direct light of today, but a dim, ruddy glow. From the surface of one of Saturn's moons, the red giant sun would fill a large portion of the sky, perhaps 10 times wider than the sun appears from Earth today. but it would not be blindingly bright. It would be a vast, deep red orb with a clearly visible disk, bathing the landscape in an eerie crimson light. This change in color also means a change in the type of radiation. The red giant will emit most of its energy in the infrared part of the spectrum. This is heat radiation. The planets will be baked by this intense infrared glow. The visible light, while coming from a huge source, will be less intense than what we are used to. It would be a dim, hot world. This red phase will last for a few 100 million years. It is the long, dramatic twilight of the sun's life, a period when it changes from a modest yellow dwarf into a colossal, luminous red star that dominates the sky and reshapes the entire solar system. Number 5, the length of a year will change. A planet's orbital period, the length of its year, is determined by the size of its orbit and the speed at which it travels. According to Kepler's third law, a larger orbit results in a longer year. As the sun loses mass and the planets move into larger orbits, their years will get longer. For Earth, if it survives at an orbit of 1.5 AU, its year would increase from 365 days to about 670 days. We take the length of our year for granted. It is a fundamental rhythm of our planet's existence. But this too will change as the sun dies. The change is a direct consequence of the laws of orbital mechanics. As the sun swells into a red giant, it will lose a significant portion of its mass through a powerful stellar wind. And a star with less mass has a weaker gravitational pull. Because the planets will be held less tightly, their orbits will expand. They will spiral outwards into new, larger orbits. A planet in a larger orbit must travel a greater distance to complete one revolution around its star. Furthermore, its orbital speed will be slower because the star's gravitational pull is weaker at that greater distance. The combination of a longer path and a slower speed means that the time it takes to complete one orbit, the length of a year will increase. For every planet that survives, the year will become longer. Let's consider Mars. Its current year is about 687 Earth days. As it migrates outwards into a new, stable orbit around the white dwarf sun, its year could stretch to over 1,300 Earth days. Jupiter's year, currently about 12 Earth years, could become more than 20 Earth years long. This change will be gradual, happening over the millions of years that the sun is shedding its mass. The celestial clockwork of the solar system will slow down. The familiar periods of the planet's orbits will be erased and rewritten. This will have subtle effects on the long-term stability of the system. The new orbital periods will create new resonances, new gravitational sweet spots, and danger zones. The slow, stately dance of the planets will adopt a new, more languid tempo set by the weaker gravity of their dying star. In the final state of the solar system, with a few frozen planets orbiting a distant white dwarf, the years will be incredibly long, markers of time in a place where nothing of consequence happens anymore. Number 4. A new habitable zone is created. The current habitable zone of our solar system is roughly between 0.95 and 1.67 AU. During the sun's peak luminosity as a red giant, the habitable zone will shift outwards to a distance between 49 and 70 AU. This is the region currently occupied by the Kuiper Belt, including objects like Pluto and Eris. The concept of a habitable zone is not fixed. It is defined by the star. As the star changes, the zone moves. When our sun becomes a red giant, its habitable zone will be completely redrawn. As the sun's luminosity swells to thousands of times its current level, the region near Earth and Mars will become hellishly hot, far too hot for liquid water. The new habitable zone, the new region where temperatures are just right, will be pushed out into the frigid depths of the outer solar system. For a few 100 million years, the prime real estate in our solar system will be the area around what are now the orbits of Uranus and Neptune, and even further out into the Kuiper Belt. This means that worlds we consider to be utterly inhospitable ice balls could briefly have the conditions for liquid water. Pluto, with its thin nitrogen atmosphere and mountains of water ice, will warm up. Its surface temperature could rise from its current 229 degrees Celsius to a balmy, Earth-like temperature. Its nitrogen and methane ices would form a thick atmosphere, and its water ice crust could melt to form a global ocean. Other large Kuiper Belt objects like Eris, Sedna, and Makemake could undergo similar transformations. They could become a chain of small, distant ocean worlds orbiting a giant red sun. This is a startling thought. The most distant, coldest, and most primitive parts of our solar system will have a brief, glorious moment of habitability. It is a final, improbable chance for life's precursor chemistry to occur. However, the conditions would be strange. The light from the red giant sun would be dim and red, and these worlds are small, with low gravity, making it difficult for them to hold onto their newly formed atmospheres against the onslaught of the red giant's powerful stellar wind. So, while a new habitable zone will be created, it will be a temporary and likely dangerous place. It represents the last geographical region in our solar system to get a turn at potentially hosting liquid water before the entire system cools and dies forever. Number 3. Venus becomes even worse. Venus is already the hottest planet in the solar system, with a surface temperature of 462 degrees Celsius, due to a runaway greenhouse effect from its incredibly thick carbon dioxide atmosphere. The atmospheric pressure on Venus is 92 times that of Earth. As the sun's luminosity increases over the next few billion years, the energy hitting Venus will also increase, pushing its already extreme conditions even further. Before the sun expands enough to swallow Venus, it will make the planet's already infernal environment significantly worse. The slow brightening of the sun during its main sequence lifetime will have a noticeable effect on Venus. While Earth is still enjoying temperate conditions, the extra energy falling on Venus will supercharge its already potent greenhouse effect. Its surface temperature will climb even higher. The thick sulfuric acid clouds will become denser and more turbulent. The planet's sluggish, 243-day rotation is thought to be the result of a thermal tide in its thick atmosphere, a braking effect caused by solar heating. The increased solar energy will strengthen this atmospheric tide, possibly slowing Venus's rotation down even further. As the sun begins its transition to a red giant, the process accelerates dramatically. The solar wind will become more intense, and it will begin to strip away the upper layers of Venus's atmosphere at a much faster rate. The planet will be cooked by a blast of heat and radiation far beyond what it endures today. Any part of the planet that isn't already molten will become so. Venus will become a glowing hot ball of rock, its thick atmosphere boiling off into space. This process will happen long before the sun's physical edge reaches the planet. Venus will be rendered uninhabitable and then physically scoured by the sun's increasing output for millions of years before it is finally consumed. It is the second planet from the sun, and it will be the second to be completely erased, but not before it is subjected to a final, intensified version of the extreme conditions that have defined it for billions of years. The story of Venus in the dying solar system is a short one. It goes from hell to oblivion. Number 2, the end of photosynthesis on Earth. The process of photosynthesis in most plants on Earth, C3 plants, begins to fail when carbon dioxide concentrations in the atmosphere fall below about 150 parts per million. As the sun gets hotter, the rate of weathering of silicate rocks on Earth's surface will increase. This weathering process pulls CO2 out of the atmosphere and locks it into minerals like calcite. In about 600 million years, this process is predicted to lower atmospheric CO2 levels below the threshold for C3 photosynthesis, leading to the extinction of most plant life. C4 plants, like corn and sugarcane, are more efficient and can survive down to about 10 ppm of CO2, but they too will die out in about 900 million years. The first major life-altering consequence of the sun's aging will not be a boiling ocean or a red giant sky. It will be starvation. The death of life on Earth will likely begin with the end of plants. This process is driven by a complex feedback loop involving the sun's heat, our atmosphere, and the Earth's geology. As the sun gradually gets hotter, the Earth's surface temperature rises. This increases the rate of water evaporation and rainfall. It also speeds up the chemical reactions between rainwater, which is slightly acidic, and silicate rocks on the continents. This chemical weathering is the primary mechanism by which carbon dioxide is removed from the atmosphere over long geological timescales. The CO2 is converted into carbonate minerals and eventually gets buried on the ocean floor. So, a hotter sun leads to faster weathering, which leads to lower levels of CO2 in the atmosphere. For a while, this acts as a planetary thermostat, keeping Earth's temperature stable. But there is a tipping point. Plants need carbon dioxide to perform photosynthesis. They are the base of nearly every food chain on the planet. When the atmospheric CO2 level drops too low, plants can no longer survive. Projections show that in about 600 million years, CO2 levels will fall below the limit for the vast majority of plant life, including trees, rice, and wheat. The great forests and grasslands of the world will die. This will trigger a mass extinction event far greater than the one that wiped out the dinosaurs. Herbivores will starve, and then the carnivores that feed on them will follow. Only the most resilient microorganisms will survive. A few 100 million years later, even the hardiest types of plants will be gone. The planet will be left to microbes and perhaps some simple animals that can survive in a world without complex vegetation. This will happen long before the oceans boil. It is a slow, silent, and inevitable consequence of our star's evolution. The very star that powers life through photosynthesis will, through its own aging, create the conditions that shut that process down for good. Number 1, the slow boiling of Earth. The sun's luminosity increases by about 1% every 100 million years. In approximately 1.1 billion years from now, this increase will be enough to push the average surface temperature of Earth to about 47 degrees Celsius. This is the tipping point where a moist greenhouse effect begins, where the stratosphere becomes saturated with water vapor, which is then rapidly lost to space. This process will evaporate Earth's oceans completely in a few 100 million years after it starts. The very first step in the end of our world will be a change in its water. The story of Earth's uninhabitability begins not with the dramatic expansion of a red giant, but with the slow, inexorable brightening of the main sequence, Sun. This process is happening right now, but it is so slow we cannot perceive it. Over the next billion years, the sun's increasing energy output will gradually heat the Earth. At first, the planet's climate systems will compensate, but eventually a critical threshold will be crossed. The rising global temperature will cause more water from the oceans to evaporate into the atmosphere. Water vapor is a powerful greenhouse gas, much more potent than carbon dioxide, so more evaporation leads to more water vapor, which traps more heat, which leads to even more evaporation. This is a runaway positive feedback loop. The atmosphere will become saturated with moisture. In the upper atmosphere, the stratosphere, this intense water vapor will be exposed to harsh ultraviolet radiation from the sun. The UV rays will break the water molecules H2O apart into their constituent hydrogen and oxygen atoms, a process called photolysis. Hydrogen, being the lightest element, will not be held by Earth's gravity and will escape into space. This process is irreversible. The Earth will begin to bleed its water away atom by atom into the void. Over hundreds of millions of years, the oceans will shrink, coastlines will recede, and vast, salt-encrusted deserts will expand to cover the planet. The climate will become incredibly hot and humid, a global steam bath. Eventually, the last of the oceans will boil away completely. Earth will be transformed into a bone-dry, searingly hot desert planet, much like Venus is today, but with a different atmospheric composition. This is the first great extinction event caused by the sun's evolution. It will wipe out all life on Earth long before the sun leaves the main sequence. It is the beginning of the end, a slow and quiet catastrophe that will unfold over 1 billion years, turning our blue planet into a dry, sterile rock.